Assalamu alaikum. My name is Hafiz Waleed Zahid, roll number 21 TE83 from Telecommunication Engineering Department UAT TAXILA. Today we perform Lab 9 of Digital Signal Processing FIR filter using window method. This is the task 1. Plot the filter in time domain along with its magnitude response. Use windowing, Hamming, Hanning and Blackman with filter and observe their magnitude responses. This is the task 1. In this code applies three different windowing functions Hamming, Hanning and Blackman to a given set of filter coefficients h and then calculates and plot the frequency magnitude response for each windowed filter. First, the filter coefficients are multiplied element-wise by each windowing function to obtain three sets of windowing filter coefficients. Then the code performs a fast Fourier transform on each set of windowed coefficients to obtain their frequency responses. The frequency responses are shifted to center around zero frequency and their magnitude are computed. Finally, the code plots and the magnitude responses of the filter with the three different windows on the same graph. Allow for a visual comparison for the effect of each winding function on the filter's frequency response. This is the output of this code. In task 2, plot the signal in time and frequency domain along with its magnitude responses. So in this code, it generates a signal composed of three sine waves with different frequencies, sum them up and then plot the signal in both the time domain and the frequency domain. The sine waves have frequencies of 500 Hz, 1500 Hz and 1700 Hz respectively. The combined signal x is plotted against the time t in the first subplot showing how the signal varies over time. The code then computes the Fourier transform of the signal x using the fast Fourier transform function, which converts the time domain signal into its frequency components. The resulting frequency domain representation is centered using FFT shift and plot in the second subplot. Showing the magnitude of each frequency component, the frequency axis is limited to the range minus 2000 Hz to 2000 Hz for better visualization of the significant frequency components. This is the output of this code. This is the B part of task 2. This code demonstrates how to use a FIR filter to reduce noise in a signal. The process starts by defining the filter coefficient h and generating a noisy input signal. The input signal is a combination of three sine waves with frequency 100 Hz, 400 Hz and 800 Hz, and it is contained with Gaussian noise and it is contaminated with Gaussian noise. The noisy signal is then filtered using the defined FIR filter h by applying the convolution property convolution operation with the same option, which keeps the output signal length the same as the input signal. The script plots the original noisy and filtered signal in the time domain using three subplots. The first subplot shows the original clean signal, the second subplot displays the noisy signal, and the third subplot presents the filtered signal and noise after noise reduction. Additionally, the script plays the three signals sequentially: original, noisy, and filter to allow auditory comparison of the noise reduction effect. So this is the output of this code. In task 3, applying application of FIR filters. This is the code. This code loads a speech signal from an audio file, processes it to filter out frequencies above 4 kHz, and then reconstructs and play both the original and filtered speech signals. The speech signal is loaded from a file named speech.wav using the audio read function, which returns the signal data and the sampling frequency fs. The fast Fourier transform of the speech signal is computed using FFT and the result is shifted using FFT shift to center the zero frequency component. The transformation converts the time domain signal into its frequency domain representation. Frequencies above 4 kHz are identified and set to 0. The frequencies array represent the frequency values corresponding to the FFT components in the indices where the absolute frequency value exceeds 4000 Hz are identified using discard indices and the corresponding FFT components are set to 0, effectively removing those frequencies from the signal. The modified frequency domain signal is transformed back to the time domain using the inverse FFT and IFFT shift. The real part of the resulting signal is taken to avoid any imaginary components that may arise from numerical inaccuracies. The original speech signal and the filtered speech signal are played sequentially using the sound function. The real function ensures that the only real part of the signal is used for playback. This is the output of this code.
You knew I would not allow it, and you did it anyway. You knew I would not allow it, and you did it anyway.
This is the last part of task 3. This code reads an audio file named music.wav and applies two different filters to it, a high-pass filter and a low-pass filter. The high-pass filter, designed with a cutoff frequency of 500 Hz and an order of 6, removes frequency below 500 Hz from the music. The low-pass filter, with a cutoff frequency of 10,000 Hz and also order of 6, removes frequency above 10,000 Hz. After designing the filters using the Butterworth filter design using function butter, the music signal is filtered by each filter using the filter function. The code then plays the original music, pauses for a second, plays the high pass filter music, pauses again, and finally plays the low pass filter music. This allows you to hear the effect of each filter on the music. This is the output of this code.